let's jump in on question 14. So for question 14, we're going to have excess HBr and heat. So this is a lot like an epoxide ring opening. So here with our oxygen, I'm going to say we've got HBr is basically acts as H+. So anytime you have an oxygen in the presence of an acid, it's going to protonate unless there's a different acid-base reaction that could take place faster. So then we end up with this plus our Br minus. If this is H plus, this is Br minus. So the Br minus is going to attack one place or the other. It does not matter because it's a symmetrical molecule. And you'll get, I'm going to keep this as much as I can. This bond broke right here. So you have an OH. And then on this side, the Br attacked. Probably should have opened that up a little bit. But here you can still see 1, 2, 3, 4. The ring structure is still sort of there. If you want, you can stretch it out into a long chain. So after the first reaction, it's going to look like this. 1, 2, 3, 4 carbons, and an OH at the end there. But we have excess HBr. So actually that same reaction can take place again. And you can end up with, I'm going to draw the Br off to this side now, with an OH that's positive. And then you've got one lone pair there. And then your Br minus from this bond breaking can come and attack again and kick this out and make it a good leaving group. So you'll end up with this. You still have 1, 2, 3, 4 carbons. So if you stretch it out, it would look like this. Let's see, is that right? 1, 2, 3, 4 carbons. Yeah, there you go. I think I drew too many on this one. Yeah, I did. I'm losing it. Okay, there you go. That's why I always number my carbons, because you can get things wrong. So the right answer is going to include the first step and the second step of addition. And so that looks like answer choice C. And actually they have a very similar one in answer choice B. If you've lost carbons or if you didn't pay attention, that there was something on the other side, you could be tricked into getting that one. Okay, number 15. If cis-2-butene is treated with MCPBA, so metachlorobenzoic acid, that's a peroxy acid, what's the final product? And that is basically just going to be epoxidation. So let's draw butene. 1, 2, 3. Cis-2-butene. 1, 2, 3, 4. It's cis. These are on the same side. If there's trans, they'd be on the opposite side. And you're going to do that with an epoxide. When that happens, your stereochemistry is maintained. So whatever's on the same side here is going to either both be wedges or both be dashes. It could be either. It does not matter. If you'd started out with trans-2-butene with the same thing, MCPBA, you would get 1 wedge and 1 dash. So the stereochemistry is basically just retained. If they're on the same side, they're going to stay the same. If they're on opposite sides, they're going to be opposites. So we had cis, so we're looking for this basically. So we're looking for something that has CH3s as both wedges, and it looks like that's answer choice A. Answer choice B is wrong because they're trans. Answer choice C is wrong because they're both on the same carbon, so that actually is, this would have to be the starting product. And here, same thing, is that would be, that would be your starting product to get that. And that's a good way to challenge yourself if you're ever feeling like that's an easy question. Maybe it is an easy question for you, but can you say why all the other answers are wrong, or work backwards and say what starting material would make this? That's a further way to challenge yourself. Okay, next question. The answer choices are on the next page, so I'm just going to draw this out here while we have some space. Trans-2-bromocyclohexanol. So the 1 is a cyclohexanol, 2 is bromo, and it's going to be opposite. One's a wedge, one's a dash. It's treated with sodium hydroxide, so that's OH minus. So the first thing that's going to happen, acid-base reaction. This is just going to deprotonate that to give us O minus and water. Now, the next thing that happens is a little weird, but it is quite literally just an SN2 reaction. This comes in and attacks, and it does backside attack, and it can make an epoxide. So this is one of two ways we've learned to make an epoxide. And see how I've inverted the stereochemistry? This was a dash, and now it's a wedge. That's because backside attack inverts stereochemistry. So this only works if you start with a trans product. If these were cis to begin with, the backside attack wouldn't work because the ring would be coming in from two different directions like this instead of like this. So it actually only works if it starts with trans. That can be a trick that happens on some exams. So the right answer would be answer choice C. Okay, this next question's a little interesting. My trick for epoxide ring opening is BLAM. Base, least, acid, most. And this ring opening, even though it's not epoxide, is going to follow similarly. So the first thing that happens if we have an oxygen with a proton is going to protonate it. So then we end up with a protonated oxygen that looks like this. Then your I minus is going to attack. So your I minus is going, this is acid catalyzed, so it's going to attack the more substituted spot, which is kind of counterintuitive. And this ring will break open. And I'm going to actually keep the kind of basic structure of the ring. And then draw this down here. That was right there. And then we have our two methyl groups and our iodine that has now attacked. So just to make sure we haven't lost any carbons, I'm going to number. We have 5, 1, 2, 3, 4, 5. So we haven't lost any carbons. So that would be how that ring opens. So the answer choice would be answer choice C. Now if we had excess, the same thing would happen that we saw a few questions ago, where this would protonate again and the iodine would replace it. But we only have one equivalent, so it's not going to keep going. It's just going to react one time. So that's the difference here between question 17 and question 14, is excess acid and heat versus one equivalent. Okay, question 18 is another epoxide ring opening. So this time it's base catalyzed, and we know it's a base because we've got that minus. So base least, acid most. So this is going to attack the least substituted side. So that's the very first thing that happens, is it attacks, and this gets kicked out. It's almost like an SN2 reaction is kind of how I think of it. And then we have, so this bond broke. So this is O minus up here. This bond broke. Down here, we have a new addition, OCH3 has attacked. So that would be the first step. And then the second step would be an addition of acid to protonate your alcohol. So I believe, oh, I forgot to, I lost a carbon, so that's not right. The OH was right, and then the OCH3. So that should be your right answer. It looks like that is answer choice A. So see, and that's why numbering carbons is so important with these, is I almost lost my carbon because I didn't number here. So you can even go and number on the answer choices if you want to, just to make sure that everything is in order. Okay, then we've got question 19. What would be the final product? And this is actually the last question. The answer choices again are on the other page. So I'll go over this quickly. So this is MCPBA. There's 2 oxygens here. A lot of times students will just see that and assume it's carboxylic acid, but if there's 3 oxygens, that is a peroxy acid of some kind, and it's going to form an epoxide. So we start out with this. It's going to form an epoxide right here. So you'll end up with this structure from the epoxidation. And then this is an acid catalyzed ring opening. So it's going to attack the more substituted side. So the first step with the acid is going to be that this, boom, boom, comes in there. And we get our protonated one. And then your, in this case, it should be this weak nucleophile, the alcohol, methanol, I don't know why I couldn't think of that, is going to come attack the more substituted side and open this ring up. So you'll end up with OH. So we've kind of got that structure still there. This bond has broken. There's 2 methyl groups already, and then an O CH3, and that had a proton that came with it, this whole structure. And that would eventually be deprotonated, and you'd end up with, I'm keeping the ring structure here, 2 carbons, 1, 2, so you've got your OH up top, and then here you have an OCH3 and 2 methyls. So that's kind of hard to see. I think you have to really keep count of your ring and keep the structure, and then once I've done that, then I'll sort of open it up to a more normal looking structure that we're used to seeing. So there's carbon 1, there's carbon 2. Carbon 1 had a methyl, a methoxy, and another methyl. So there you go. So the final product would be, oh, this is tricky to see, but I think it's answer choice C, because we've got our CH3 here with 2, a carbon that has no other, and oh no, it has an alcohol there. So, oh, it's this one here. Oh, I think technically that is answer choice. I don't know. It should be this one. These answer choices are all messed up. That's answer choice A. That's not the right answer, but that's so that you can see where answer choice A is. B goes here, and this is C. Okay, so answer choice C is the right answer. This one's not. Neither of those are. Okay. And sometimes they can show up on tests like this. I guess you guys will be taking it on the screen, but if you can make sure which one goes to what, that'll really help you out. So that's a quick review of all your practice problems from this chapter.